Roots of complex numbers. So this is a continuation of our previous discussion where we found ways of calculating roots of complex number. Now let's first summarize, have a look at the summary of the method. So given a complex number and the question is find nth roots of a given complex number. In other words, we need to solve equation u raised to power n is equal to z0. We need to find all values of u such that when we take power of u to be n, then it gives me the answer z0. Now, in the first step, we write down this complex number in the exponential form, and in the next step, we write down the most general form of this complex number in the exponential form. So in other words, we just add 2k pi in the argument of this complex number, as we have discussed in our previous discussion, that if I increase the argument of a complex number by an integer multiple of 2 pi, then it's going to give me the same complex number. And the third step, we take raise the power of this exponential form by 1 by n, and from our previous discussion, this gives me the following answer. There are 3 steps for calculating nth roots of a given complex number. Now, what is the variation of k? We discussed that the variation of k is going to be from 0 to n minus 1. So they are going to be exactly nth roots of a given complex number z0. Now, next we are going to study a very important example. It's basically the nth roots of unity. Now, our given complex number is 1. Now, if you remember that in schools, when we used to calculate cube roots of 1 and fifth roots of 1, etc., etc., then the answer was always 1. So in other words, if I calculate cube roots of 1, then the answer was 1. Now, we learned that since 1 is a complex number and there should be 3 cube roots of unity, etc. So now we are going to calculate those other roots of unity. And following the steps of our previous discussion, in the first step, we write down unity in terms of exponential form. And in the second step, we write down the most general form of this complex number. In other words, adding an integer multiple of 2 pi in the argument of this complex number. And in the third step, we raise the power of this complex number by 1 by n. So symbolically it means that we just divide 0 by n and 2k pi by n. And of course the variation of k is going to be from 0 to n minus 1. So these are all nth roots of unity. Now observe that if I take k is equal to 1, then it's going to give me this root. And if I take k is equal to 2, then there is a relation between that root with omega n. So if I take power of omega n to be 2, then it's going to give me e raised to power iota 2 pi by n multiplied by 2, which is exactly the same root that we got when k is equal to 2. So in other words, we can say that if I start from omega n, then the next root is going to be omega n raised to power 2. And the next root is going to be omega n raised to power 3, and up to so on. And if I want to get all the roots of unity, then I need to take powers of this omega n by n minus 1. And of course, when k is equal to 0, then we are always going to get 1. So this is the nth root of unity that we used to use in our schools. But then these are the other roots that we found using this method. So in short, if I have this omega n, then the roots of unity are given by 1 omega n square, up to so on, omega n raised to power n minus 1. Now this omega n, due to which we are able to calculate all of the roots of unity, is called the primitive nth root of unity. Now, let's in particular calculate square roots of unity. Now, following the steps, the number is z is equal to 1, we can write down 1 in its exponential form. So we get e raised to power iota into 0. And in the step 2, so in step 2, we write down the most general form of this z0. So it becomes e raised to power iota 0 plus 2k pi, where this k is an integer. And in step 3, we calculate z raised to power 1 by 2. So in other words, it gives me the following answer: iota 2k pi by 2, where k is integer. Now simplifying and observing that the variation of k is 0 and 1, we get the following answers. So 2 will be cancelled out with 2 and we get k pi. And the variation of k is 0 and 1. Now when k is equal to 0, then we get 1. And when k is equal to 1, we get, so the first root is going to be, for k is equal to 0, the answer is 1. And when k is equal to 1, the root is going to be minus 1. So in other words, this is 1 and this is minus 1. And this also fits with our discussion in the previous part of this series of roots of complex numbers. So what was the description? So if I am calculating the square roots of a given complex number, then they are at the opposite ends of a line segment. And in this case, we can observe that they are at the opposite ends of this line segment. Similarly, we can calculate the cube roots of unity. So in this case, of course, the complex number is the same. Z0 is equal to 1. And we can write down this complex number. Following the steps, we can write down its exponential form, and then writing down this complex number in the most general form, and then raising the power to 1 by 3. We'll be able to get the following cube roots of unity. So the first root is always going to be 1, and when k is equal to 1, we are going to get the following root: minus 1 by 2 plus iota square root 3 by 2. And the third root of 1 is going to be minus 1 by 2 minus iota square root 3 by 2. So these are three roots, three cube roots of unity. Now let's discuss the geometry of these three roots. So this is 1, and this, which is another cube root of unity. So this is minus 1 by 2 plus iota square root 3 by 2. And this is the third root of third cube root of unity, which is minus 1 by 2 minus iota square root 3 by 2. And we can also observe that all of them lie on a circle of radius 1, and they are also vertices of a regular triangle, and up to so on. Now let's discuss in general the geometry of these nth roots of unity. So when n is equal to 1, we get 1 root, and when n is equal to 2, we get 2 roots. They are at the opposite ends of this line segment. When n is equal to 3, we get 3 roots, which are the vertices of a regular triangle. And when n is equal to 4, that they are vertices of a square, and of course they lie on a unit circle. And when we increase n, we'll be getting more and more roots, but two properties are very fixed for these roots. So the first property is all of them lie on a unit circle. Okay, so all of them lie on a circle of radius 1. And the second property is they are vertices of a polygon. And of course, one of the important observation is one of the root is always going to be 1. So this is basically your we can say the starting point. Now our next discussion is the relation between roots of any complex number and the roots of unity. Now we know that from our previous discussion that the nth roots of any given complex number z0 can be calculated using this formula. Okay. Now we can expand this formula in the following form. So this is the first part and this is the second part. Now this second part is basically the roots of unity. When we vary k, then we'll be getting the nth roots of unity. So in other words, we can say that whenever we have nth roots of a given complex number, then we can write them down in the following way. Okay, so this expression multiplied with the nth roots of unity. Now this in particular is just one nth root of this complex number z0. Let's call it c0. Okay, so but the rest of the nth roots of this complex numbers can be obtained by multiplying nth roots of unity with this c0. So if we know nth roots of unity and just one nth root of a complex number z0, then we can calculate all of the nth roots of a complex number. So in general, if zeta is one of the nth roots of z0, then the other nth roots of this z0 can be calculated by multiplying zeta with nth roots of unity. Now let's apply this observation to calculate cube roots of 2 iota. If we want to calculate the cube roots of 2 iota, we need to write it down in the exponential form first. So the exponential form becomes 2 cosine pi by 2 plus iota sine pi by 2. In the second step, we write down this z0 in the most general form. So that is, it becomes 2 e raised to power iota pi by 2. Okay, so z0 equals 2 e raised to power iota pi by 2 plus 2k pi, and this k is integer. And in the third step, we just take the power to be 1 by 3. So in other words, this becomes cube root of 2, and we multiply the power of e with 1 by 3. So we get the following expression. Here k is an integer. So in other words, we can say that these cube roots of 2 iota becomes cube root of 2 multiplied with e raised to power iota pi by 6 2k pi by 3, where k varies from 0, 1 and 2. Okay, so there should be 2. Now the first root is cube root of 2 multiplied with iota pi by 6, and we don't need to calculate the rest of the roots of 2 iota because we can just multiply c0 with cube roots of 1 and we will be able to get the rest of the roots of 2i. So in other words, c1 will be equal to c0 into omega 3, c2 will be equal to c0 omega 3 square. Now since we can calculate the square root, cube roots and in general nth roots of any given complex number, now let's have a look at the quadratic formula again. Now remember, when in schools where there was a symbol like square root of -1, then we just left it, that it is not defined. Now we can calculate square root of any complex number, which includes -1, which includes iota and other complex numbers. So that is why we are going to revisit this quadratic formula again, and let's see what are the facilities available to us now, using which we can calculate or we can apply quadratic formula on any quadratic equation. Now given this quadratic equation, so in this quadratic equation, or a is equal to 1, b is equal to 2 plus iota, and c is equal to 3 by 4. So quadratic formula is the same, but now the point is b square minus 4ac is going to be a complex number. Now we know that there is a square root in the formula on b square minus 4ac, and we know that we can calculate the square roots of any complex number. Now let's apply that method of calculating square roots of any complex number. Okay, so in this case, this is the discriminant. if we simplify this thing, then the discriminant becomes, okay, so this part is basically the discriminant, and in this case the discriminant is 4 iota, and we want to calculate the square roots of 4 iota. So using our previous discussion, we can easily calculate the square roots of 4 iota to be square root 2 plus iota square root 2 minus square root 2 minus iota square root 2. Now using these two values of square root of 4 iota, we can easily calculate the roots or roots of this quadratic equation, or we can say that the solution of this equation. Okay, so the roots, we are just replacing the square roots of 4 iota in place of b square minus 4ac square root. So this is the first root and this is the second root. So this is the first solution and this is the second solution of this equation. Now in this discussion, we applied the techniques of nth roots of complex number to explore about roots of unity, and then we further explored the relation between roots of unity and roots of any complex number. And we also observed that